Okay, hello everybody. In today's class, we will do few problems related to the theory which we have learned so far in terms of several steps of modeling. So, I start with the question which I had asked you last time. So, starting from a lossless pendulum for which the equations look like this, right, where theta was the angular displacement and theta double dot plus g over L sin theta was equal to 0. Okay. And this represented a simple harmonic motion. Is there an electrical analog of such a behavior or such dynamics? Well, let us take this circuit with L and a C, right. So, if I write down the voltage loss, I will have L di by dt plus 1 over C integral I dt is 0, right. Or if I write it in terms of the charge, I will have L d2 q by dt square plus q over C is equal to 0. Okay. So, the solution to this will be periodic, right, in the same way as it will be to these equations. Only difference here is that I am just using both of them are linear elements. So, here the sinusoidal term comes because of the non-linearity of the element. Of course, we will discuss about the relation between this model and this model when we do linearization of nonlinear systems, but solutions to both of them will just be periodic, right. And when we had the lossless or the pendulum with some friction element, we had an additional term. So, my equations look like theta double dot plus g over L sin theta plus b theta dot was equal to 0, and analogous here would just be an RLC circuit. So, I just add a resistance R, so this is an L, a R and a C, and my equations would just be L d2q by dt square plus R times q dot plus q over C equal to 0, right. And then the behavior again is the same. This is again I am just ignoring the nonlinear element here for the while, but the linear version of this would look something like this, and this is the analogous behavior of the simple pendulum in the mechanical system case. Okay. So, we will do some more examples related to this. Okay. So, let us take a system which looks like this. So, all this is my reference points or the reference node as I would call it. I have a mass which I call M1 and which goes around this surface. Between the mass and the reference point is a spring with constant K1. There is another mass M2, right, and between these two masses is a damper with its value B12, a spring connecting these two masses with spring constants K12. The friction of this surface is B1, the friction over this is B2, right, and there is an external force which is being applied here called F, which results in a displacement here. I will denote this as x2, and this displacement I will denote as x1. Okay. And then my problem here, or what I want to write, is the dynamical equations governing the system or the model of this system. Okay. So, if I go through the steps of the modeling, the first thing to do is to identify the number of displacements right. In this case it is x1 and x2. So, the number of displacements is 2. Then what are the nodes? Right. If I follow the steps, I would choose x1 and x2 as my nodes together with a reference node. Okay. So, if I just mark my nodes here, I call this x1 and let me call this x2 and maybe a reference node here. Okay. Now, if I look at each of my element, right, the first element M1 is between x1 and the reference node, right. So, I will just draw it this way. So, x1 and the reference node in between is M1. Okay. Now, look at even K1. K1 is also between x1 and the reference node. So, I could draw it. Okay. And similarly also with B1. So, the B1, the damping element would show up here. Right, call this B1. Okay. Now, between the nodes x1 and x2 is a dashpot or a damping element or and also a spring. So, I would write this as a spring. So, between x1 and x2 the damping element and a spring with coefficients B12 and K12. Okay. Now, I go to node number 2. There is a mass between node number 2 and the reference. Similarly, a damping element here. So, that would look something like this. So, between this there is a mass M2, there is the frictional element denoted B2 and there is a force which is being applied, which looks like this. Okay. Now, once we have the system written in form of its nodal components, then it is easy for me to write down the dynamics, or I just write down the conservation laws at node 1, right. Node 1 where I have the mass, a spring, a damper, or actually node x1, right. So, okay, how will the equations look like? All the forces corresponding to each of these elements, this would be M1 x1 double dot plus this is modeled as k times x, the damper goes like B1 x1 dot, that takes care of these 3 elements. Through node 2 there are also these other 2 elements and these equations would be B12 x1 dot minus x2 dot plus K12 x1 minus x2 is 0, right. So, the sum of all the forces here is 0. Okay. Now, I look at the second node, node 2 or denoted by x2, right. We have an input force, force of this guy over here, force of the mass and these 2 elements, right. Okay. So, this would just look like F is M2 x2 double dot plus B2 x2 dot corresponding to this element and I have these 2 guys here B12 now with x2 dot minus x1 dot plus K12 x2 minus x1, right. The sum of all the forces here is equal to the external force which is being applied through F, right. So, these are the entire equations which govern the dynamics of the system. Okay. So, we also learned how to write this in the force voltage analogy and also the force to current analogy. Okay. So, let us just recollect how these analogies look like. Okay. So, here we learned the analogy between electrical and mechanical systems via the force voltage analogy and also the force current analogy. So, let us draw this equivalent mechanical system in terms of its force, say starting with voltage analogy. Okay. So, the force to voltage analogy tells me that force is related to the voltage, mass with an inductive element, friction with a resistor, spring with a capacitor with 1 over c being the value. Okay. So, if I just use those directly, my equations, okay, let us write down the equations first, that might help us drawing the picture a little better. So, M becomes L1. The basic elements here are the displacement will be mapped to the charge. So, I have L1 Q1 double dot plus R1 Q1 dot plus Q1 over C plus R12 Q1 minus Q2 plus 1 over C12 Q1 minus Q2, right. So, the mass is replaced by this inductor B1 by R1, okay, K1 by 1 over C. You can look at the analogy table why this is 1 over C. Then R12 replaced is represents B12 and 1 over C12 represents K12, all this equating to 0. Okay. The second equation would look like the force would be analogous to a voltage L2 Q2 double dot R2 Q2 dot plus R12 Q2 dot minus Q1 dot. Okay, I am sorry, there will be a dot here as well, right, because of the x1 dot minus x2 dot will transform to q1 dot minus q2 dot, right, plus 1 over C12 q2 minus q1. Okay. Now, if I were to draw the equivalent circuit, well, I have the voltage source V, which is an analogy of the force, then I will have R2 L2 representing the mass M2, then these two elements B12 and K12 would look something like this. I have a R12 C12 and then the mass M1 with L1, the element B1 with R1 and the spring K1 is analogous to C1. Okay. So, if I write down, treat of this as a circuit, right, and then write down the equations with possibly maybe this directions of current, I just get these two equations, right, and this is essentially the force to voltage analogy, right. Similarly, we could also write down the force to current analogy. Okay, in the force to current analogy, my force is analogous to current, mass instead of an inductor now is analogous to a capacitor, the friction element is now a conductor, spring is now equivalent to an inductor, and the displacement is now analogous to a flux element, right. Okay. So, let us see how the first equation goes. M1 x1 double dot plus k1 x1 b1 x1 dot b1 2 x1 dot minus x2 dot plus k1 2 x1 minus x2 going to 0. Okay. So, M1 from the table would represent the capacitor C1, x is equivalent to the flux phi, I will call it phi 1 double dot plus the spring element is equivalent now to an inductor, I will have 1 over L phi 1. Now, with the resistor I will have 1 over R 1 phi 1 dot plus 1 over R 1 2 phi 1 2 sorry phi 1 dot minus phi 2 dot plus 1 over L 1 2 of phi 1 minus phi 2, all this is equal to 0. Okay. Now, look at the dimensions of all these have dimensions of current. So, I am just writing down a current conservation law at a particular node. Earlier I had written down the voltage conservation law. Similarly, the second equation, my source F is equivalent to a current, and again going back to the analogy table, I can write down the equations in the following way. Okay. So, how would this look like in the circuit diagram? The mass, I will start with the mass, will be replaced by C1, then I have the spring with L1, B1 replaced with R1, then I have these two elements here, okay. So, this is R12, L12, then I have the other three elements following, right. The current source, I have M2 replaced with C2 and B2 replaced with R2, and this is my equivalent circuit in the Fi analogy, right. So, we started with a system, we had it in a form where we could write equations with node 1 and node 2, just the summation of all the forces is 0. Then we came to the force voltage analogy using the table and the force current analogy, right, and we could even come up with the equivalent circuits. Okay. So, the second example is a motor driving a load through a gear train. Okay, so how does this look like? Okay, let me denote this block as my motor, okay, with this motor is connected to a gear train and this gear train is then in turn connected to a load. Okay. Okay. So, the motor produces a torque Tm, right. I will also denote the moment of inertia here as J1, right. The displacement as theta 1 again in this direction, right, and a friction coefficient d1 over here. Okay. Similarly, here if this is moving this way, theta 2 will go in this direction, right. Imagine this as a gear rotating this way, then this will force it to rotate the other way, okay. And then there will be a certain load torque. Okay. Now, this gear has a radius of r1 with the number of teeth, if I may call, as n1. Here it is r2 and n2, right. So, I can call this as the primary and secondary, right, analogous to what I call in the transformer. Okay. Now, I want to write down the dynamical equations for this or the model for this. Okay. So, start with the motor shaft thing first. Okay. What are the elements here? Well, the motor generates or gives me this torque Tm. Now, I have J1 theta 1 double dot, right, plus d1 theta 1 dot. Okay. Now, this would be the dynamics if there is no load or there is no gear train also, right. So, the input power would be consumed by the inertia here, the J1 and the frictional element. Now, what this load does is, well, it requires some torque, and how is this torque reflected here? It is reflected via this gear train to something here. So, there will be additional torque which is experienced here or additional load because of or additional torque because of the load. Let me denote this as TL. So, Tm now compensates for J, D or J1, D1 and also this TL, right. Okay, I will not call this TL, I will say I will call this T1. Okay. This TL is reflected here through the gear train as T1. Okay. So, I will have a T1 here. Okay. Now, at the load side, okay, so I have a J2 here and a D2. Similarly, I have J1 and D1 here. Okay. So, here this T1 is experienced here as some T2, right. I will tell you the relation between T1 and T2 shortly. So, here I have the term corresponding to J2 as J2 theta 2 double dot, then I have the friction element here theta 2 dot plus I have the load torque TL. So, where does all this come from? So, I have to compensate for the load, compensate for J2, compensate for D2, and this comes via T1 through the gear train, and let me call this as T2. Okay. Or let us see the entire process here, right. So, I have Tm, the motor torque, it first compensates for J1 and D1 and gives me a torque T1 here. This T1 is transferred via the gear train to the secondary side called T2, and this T2 has to compensate for the load, compensate for D2 and compensate for J2, right. And each of these models which we had seen earlier, right, why is this J2 theta 2 double dot, why is this D2 theta dot and so on. Okay. Now, what is the relation between T1, T2, R1 and 1 and R2 and 2? So, we will use the relation that the linear distance travelled by both the gears is the same, which means theta 1 times R 1 is theta 2 times R 2. Okay. Since the linear distance travelled by both the gears is the same, I have that theta 2 by theta 1 is R 1 over R 2 is N 1 over N 2. Okay. Further, I assume that in the transfer of power between the primary side of the gear to the secondary side, there is no power loss, which means T 1 theta 1 is T 2 theta 2. Now, this means that T 1 over T 2 is theta 2 over theta 1 is N 1 over N 2. Okay. Now, the relationship here can also be written in the following way, that theta 2 double dot, theta 1 double dot, the angular acceleration, the angular velocity is N 1 over N 2. Okay. Now, T 1 can be written as N 1 over N 2 times T 2. Okay. Now, what is T 2? T 2 is J 2 theta 2 double dot d 2 theta 2 dot plus T L. So, the relationship between T 1 and T 2 is given by substituting for T 2 over here, that is J 2 theta 2 double dot plus d 2 theta 2 dot plus T L. Okay. Now, substituting for this T 1 in this equation gives me the following, that T m is J 1 theta 1 double dot, this one, plus d 1 theta 1 dot plus T 1. So, I am substituting for T 1 here, that is N 1 over N 2 J 2 theta 2 double dot plus d 2 theta 2 dot plus T L. Okay. Now, from this expression I can rewrite this expression again in everything in terms of theta 1, right. I have to write everything theta 1 or theta 1 double dot and theta 1 dot. So, this will look like the following, J 1 theta 1 double dot, okay, let us take this term, right. J 2 theta 2 double dot is, in terms of theta 1 would be J 2, again from this expression. What is theta 2 double dot? Theta 2 double dot is N 1 over N 2 theta 1 double dot, right. So, J 2 theta 2 double dot would be J2 theta 1 double dot with N1 over N2. Okay. Now, here I have N1 over N2 J2 theta 2 double dot. Therefore, N1 over N2 J2 theta 2 double dot would simply become this guy. Okay. Now, there is this term corresponding to theta 1 double dot, and also J2 theta 2 double dot can be written in terms of theta 1 double dot. So, substituting for this guy over here, I get the following. So, I have J1 plus J2 N1 by N2 whole square times theta 1 double dot. Okay. Similarly, I could do for the second term, right? I can write d2 theta 2 dot in terms of theta 1, right? We are just using the relation that theta 2 dot is theta 1 dot N1 over N2, which means N1 over N2, here N1 over N2 d2 theta 2 dot is d2, what is theta 2 dot? Theta 2 dot is N1 over N2 theta 1 dot. So, I have theta 1 dot N1 over N2 square. Okay. So, the second term would be d1 plus N1 by N2 square d2 theta 1 dot plus, now the remaining term is N1 over N2 times TL. All this is equal to Tm. Okay. Now, I can call this J equivalent. I can call this entire guy as D equivalent and write down my overall equations this, that J, or is called J1 equivalent, D1 equivalent, at J1 equivalent theta 1 double dot plus D1 equivalent theta 1 dot plus N1 over N2 TL is Tm, right. So, this is the dynamics referred to the motor shaft. And if you remember something from transformers, this would also resemble the equivalent circuit dynamics referred to the primary side. Okay. Now, I could also do it referred to the load shaft. Where I will just write down the equations. So, you will have J2 equivalent theta 2 double dot, where I just want to write down all equations now in terms of, or this one, this equation in terms of not theta 1 double dot, but now in terms of theta 2 double dot plus D2 equivalent theta 2 double dot plus the TL would remain as it is and Tm would get transformed via the gear ratio to N2 over N1 of Tm. It is exactly the same procedure which we did here in terms of writing in theta 1 double dot, we just write in theta 2 double dot using these relations and the first two equations which govern the dynamics. Okay. So, these are two ways of writing down the entire equations of motion of this one referred to what we in the transformer terminology call as the primary side or the motor shaft in this case, or refer to the secondary side or as the load shaft in this case. Sorry. Okay, sorry. Okay, sorry. This will be theta 2 dot. Thanks for correcting that. Okay. So, this will be J2 theta 2 double dot, D2 will come always with a theta 2 dot plus TL is N2 by N1 Tm. Okay. So, thank you for attention.